Swayam Prabha. Digital India. Educated India.
I want to talk in this one about a very interesting thing is what is uniform random distribution. Now here I am talking about, suppose particles. So look at this picture. Here in a 2D, these particles are uniformly distributed. When I say uniform, it's not on a lattice, it's random, but the probability of finding more in some region, it's not there. Everything gets equal probability. It's sort of like I tell you, throw your marble in the sand pit anywhere, no preference. Okay, so you throw a marble, then you throw another marble, and if you distribute it, it will be like this. But if I give you million marbles and you throw them, and you come back, pick all of them and throw again, next time it won't be the same. Every time it will be different. Okay. Now one of the interesting thing is that now let's say coarse grain it. In other words, we take a volume and we count how many marbles or particles are there in any volume. Now I want you to think going from very small sample volume to very large sample volume. Now if the volume that you look at where you're coarse graining, if it is small, you will get tremendous fluctuation. Let's say it's really tiny. So you may have one particle in there or none, 0 or 1. It will be a big variation. So the mean will be, even if it is some value, the fluctuation will be tremendous. But if you make it bigger, then you may say, well, there is 100, maybe 105, maybe 98. Still it's a random variable, but the variation starts becoming small. Now if you take even bigger volume, there is a million in there, million plus or minus 1,000 becomes very, very small. So the lesson is, the larger the number of particles, the variation will get smaller and smaller and smaller. That's the main thing that I wanted to point out. The second thing is that I first already talked about what is uniform random distribution. That means it's not lattice, it is. Even if it is uniformly random distributed, if you take sample volumes, there will be fluctuations. Okay, those are the two main lessons I wanted to convey in this lecture. Let's go through a little bit of details. I already filled in these things. So it follows what is called a Poisson statistics. That's what I wanted to convey. But this is a very important thing, because later we will ask, when somebody gives you a random distribution of particles, a fair question is, hey, my model is good for uniform random distribution. Is my application really uniform random distribution? If the answer is yes, then you can use that model. If your distribution is highly clustered, like there is a clump here, there is a clump there, what right do we have to use the same model that people have developed for uniform random distribution? So we have to sort of worry a bit, try to develop a new model, or what have you. You have to. So that's the kind of question that I'm trying to ask is, how particles are distributed is of great importance, and we want to have a measure of it. And what are those measures is what we are going to talk about in the next few lectures. So going back to this, let's say this whole volume, this cloud's volume is big omega, and let's say there are n omega, large number, millions of particles in there. But now I want to coarse grain, and I want to just look at a volume, the script v. Okay. So I want to know how many particles are there in that little volume. Now how many particles in this whole volume is a deterministic number, that I tell you there is a million particles. But if I ask you how many particles are in this any volume of size v, in a real experiment, if I fix that volume as flow comes in and goes out, it will be a random number, maybe 100, maybe next instance it will be 98. So it's a random number, it's a random variable. Okay. The number of particles inside this little volume, sub-volume, is a random number. Okay. So, now the question we want to know is, if I were to take the size volume, but I put it at many different places or many different times, what's the average number of particles inside this? So, this angle brackets is the ensemble average. That is easy to know, because now I have done averaging. So, on average I am going to have the total number of particles divided by the total volume, that is the volume fraction, times the volume that I am sampling. Okay. So, in other words, even though at any instant when I ask how many particles are there in this tiny red volume, that keeps changing. But if I average over time, or if I average over different such volumes, it becomes a regular deterministic number again. Okay. Now, I can go through these details, but they are not very important. So, I am trying to calculate what is the probability, how many particles are going to be in here. What is the probability having 1 particle in there, 2 particles in there, what is the probability of 5 particles in there, like that. If you calculate that, that is easy to calculate, because it is simple mathematics. You say what is the probability of 1 particle being inside that volume. That basically is that is that volume of this tiny sampling volume divided by the whole volume. So, that is what, and which is also can be written in this ratio. So, that is the probability of finding 1 particle, and the probability of not finding 1 particle, that 1 particle will be 1 minus that is the complementary. So, what is the probability of finding exactly k particle? You have to find this to the raised to the power k, and this raised to all the particles minus k. So, in other words, you can calculate precisely what is the probability of having k particles inside this volume, given that there are n omega particles in the whole volume. You can find, and it follows what is called a Poisson distribution. So, the important lesson is, again, as I mentioned at the beginning, if we cut out all these math, not very good after lunch, a good lunch. But the main picture is that when you take a sub volume and you start asking a question, how many particles in there, it is a random number, and that random number follows Poisson statistics. Okay. And the Poisson statistics will look like this. Okay. So, this dash curve is the probability if the average is 5. If the average is 5, of course, the likelihood of seeing 5 is very high, but you can also sometimes see 4, sometimes 3, sometimes 2, but probably very seldom you will see 100 particles if the average is only 5. Okay. Now, this one, this solid curve is written Poisson distribution for average being 10. So, seeing average 10 or 11 particles is very large, but you will not see 1 particle or 25 particles that easily. Okay. So, that is the natural distribution. The important thing is that if the mean, if some number, the standard deviation is square root of that. Okay. So, that is why when you have 1 particle, standard deviation is square root of 1, which is 1. So, you might see it, you may not see it, sometimes you will see 2. Okay. But if you do 100, square root of 100 is 10. So, that variation is only plus or minus 10, 100 plus or minus 90 to 110, that is not that bad. If you have a million, it's million plus 1000. So, in other words, the more the particles, the spread becomes comparatively smaller and smaller and smaller. So, that is the typical Poisson distribution I want you to think about. So, larger the sampling volume, larger the mean, and lower the relative fluctuation. Okay. So, this is what some Professor Pushpavanam asked, what is the volume averaging? It should be fairly large, that you have many particles, therefore, the standard deviation will be low. Not only this, volume fraction follows Poisson distribution, number density follows Poisson distribution, all of them follow Poisson distribution. Okay.
So, if size of the particle are not same, then can we do the same for a size distribution also?
For different size particles? I don't know the answer to that question. Okay. I will have to think about it. Good question. So, typically you might want to break it into bins, size between 1 micron to 5 micron, 5 microns to 15 micron, some way you divide that, then it becomes mono dispersed within each bin, and you can ask this question. Now, your question, though I am not able to answer, precisely what the answer is. I don't know. It leads to another interesting thing is that all these statistics are good only for very low volume fraction. Okay. Now, when I said I give you 1,000,000 particles and you throw in the sandbox, okay, you can throw them. If they're all really tiny, you can scatter them all over. Okay. They're like mustard seeds. You just throw them all over. They don't. But on the other hand, if all of them are pretty big, then once you put one, you can't put another one on that same spot. You got to put somewhere else. So in other words, when the volume fraction increases, when the particle starts occupying 1% of the volume or 10% of the volume, Poisson statistics is only approximate. So the Poisson statistics is only for point particles. Okay. So, but the actual statistics is close to Poisson statistics as long as the volume fraction is not very large. Okay. Now, in this slide, I just wanted to make you think about creating this uniform distribution is not that easy always. Okay. What people use is what is called sequential random insertion. So, you have many marbles and I tell you please randomly distribute in a box, in a 2D box, let's say. You put the particle somewhere first, then you again choose a random position, and before you put, you want to ask, do I clash with the ones that are already there? Because you can't put them on there if they are of finite size. Then if they clash, then you have to pick another random number and then place it, and you keep doing that. And you can do this for 20% volume fraction, 30%. But when it becomes really very dense, then you can't add any more, because every time you choose a number, it's already overlapping on somebody, so you have to reject it. Okay. So there are some complexities happen. The other thing is that collisional equilibrium, that's the other technique that you use. I mean, creating random distribution is not easy. So if you want to create a 40% random distribution, what you usually do is you create a structured array, okay, a lattice array of 40% volume fraction, and then set all the particles in random motion, and you make them collide, bounce, like a billiard ball kind of thing. You let them bounce into each other for some time, and then you stop and say that's your random distribution. So that's one way to create it. The other thing is that swelling algorithm. So in other words, you put smaller particles, start only 10% volume fraction, you distribute it, and then start making the particle bigger and bigger. Maybe they will try to push each other a little bit, you let them do. So creating a uniform random distribution is a challenging job. But we need to do that because we want to study precise systems so that we can make conclusions. So creating uniform random distribution is a very canonical system that we study all the time. Okay. Now remember, earlier we talked about particles being spun out of vortices, etc. So many systems will not be uniformly random distributed. Okay. But you might take a local region where it could be nearly uniform. So uniform random distribution is a good theoretical concept, and we want to use it, but use it with caution.